Hello, welcome to chapter 13. This is section 13.1. It's called Trigonometric Identities, as you should see on your note guide. So what we did in chapter 12 when we started trigonometry is we evaluated different trigonometric functions. We learned about sine, cosine, tangent, secant, cosecant, and cotangent, and all of that good stuff. So what we're going to talk about in this section is something called a trigonometric identity. And in this section, we're focusing on two skills. We're going to be finding values using identities, and we're going to simplify expressions using identities. So the new vocab in this section is basically just trigonometric identity. Okay? So the first skill that we're focusing on is finding trigonometric values. So ignore this thing about the equation. We're going to get back to it in a second. A trigonometric identity is an equation. It involves trig functions, and it's true for every value that our equation is defined at. Okay, so it's an equation that is always true as long as the angles you're plugging in make it defined. If I can show that there's a specific value I can plug in that makes it false, then I found a counterexample, and it's not an identity. An identity is an equation that is always true. So for example, 2x equals 7. This is not an identity because x can only have one value, right? 7 halves. This is not true for every value of x. So this would not be an identity. It's just an equation. Here we have a bunch of basic trigonometric identities. Some of these you already know. You already know that tangent is sine over cosine. This is true for every value where it is defined. Remember, wherever cosine would be 0, this would not work, but that's okay. It's for every angle that I plug in that cosine is not 0, tangent is equal to sine over cosine. Cotangent is equal to cosine over sine as long as the sine of theta is not equal to 0. Remember, these are also identities you should already know. Sine is 1 over cosecant. Cosine is 1 over secant. Tangent is 1 over cotangent. Cosecant is 1 over sine. Secant is 1 over cosine. And cotangent is 1 over tangent. Those are ones you should already know. The Pythagorean identities are super basic identities that get used all of the time. So the cosine squared of theta plus the sine squared of theta is always going to equal 1. So I'm going to show you a specific example that shows why this is true. If I take 30 degrees as the angle I'm plugging in for theta, the cosine of 30 degrees is the square root of 3 over 2. So square root of 3 over 2 squared. The sine of 30 degrees is 1/2, so 1/2 squared. Square root of 3 over 2 squared is 3/4. 1/2 squared is 1/4. When I add those together, I do get 1. It just so happens that this is true for all angles. The cosine squared plus the sine squared of a specific angle is equal to 1. Then I have an identity with tangent and secant. Tangent squared of theta plus 1 is equal to secant squared, and cotangent squared plus 1 is equal to cosecant squared. These are super important identities that you need to know. The cofunction identities are basically just saying that with left and right translations with horizontal shifts, we can make sine and cosine equal. So the sine of pi over 2 minus theta, remember pi over 2 is 90 degrees, so 90 degrees minus theta takes me to the cosine of that angle. That makes sense because we know that sine and cosine, if we think about their graphs, are just shifted to the left or the right by 90 degrees. So the cosine identity is very similar. Cosine of 90 degrees, or pi over 2 minus theta, is equal to sine. And then tangent and cotangent work the same way. Then we also have something called the negative angle identities. The sine of negative theta is equal to the negative sine of theta. So if I take the sine of negative 30, these two expressions would be equal. The sine of negative 30 degrees, I know it would be in the fourth quadrant, so it would be negative 1/2. That's the same as the sine of 30, which is 1/2 times negative 1. But the cosine of negative theta is equal to the cosine of theta. So the cosine of negative 30 degrees, that would be the fourth quadrant where cosine is positive, so that would be square root of 3 over 2. That's the same as just the cosine of 30 degrees in the first quadrant, which is square root of 3 over 2. All right, so take a look here. This is an example of what I was saying, that identities are only true where they're defined. So this identity, tangent of theta is sine of theta over cosine theta, is true except for 90 degrees, 270 degrees, etc. Because the cosine of 90 is 0, the cosine of 270 is 0, so that would make this not true. But it's true everywhere where this is defined. Okay? Now what I'm going to show you now is how to use identities to get those exact values of trig functions. So we're going to find the tangent of theta if we know that the secant of theta is -2, and we know that theta is between 180 degrees and 270 degrees, which means it's in quadrant 3. So I'm going to look for an identity that relates tangent and secant. So you go back to your chart and we find this trig identity. It's one of the Pythagorean identities, that the tangent squared plus 1 is equal to secant squared. So I'm going to subtract the 1 from both sides. And then I'm going to plug in what I know. I know that the secant of theta is -2, so the secant squared of theta is -2 quantity squared. Substitute it in, and I just simplify. So -2 quantity squared is 4. 4 minus 1 is 3, so I have tangent squared of theta is equal to 3. Then I take the square root of both sides, don't forget to do plus or minus, and I get the tangent of theta is plus or minus 3. Since I'm in the third quadrant, tangent has to be positive, thinking back to chapter 12. So I'm going to choose positive square root of 3 because of where my angle is, because of what quadrant it's in. So here's another one with sine and cosine. Find the sine of theta if I know that the cosine of theta is -1/2. And this time theta is from 90 degrees to 180 degrees. So I'm in the second quadrant. Look for an identity that relates sine and cosine. So this Pythagorean identity works. Substitute what I know. I know the cosine of theta is -1/2, so cosine squared of theta is -1/2 squared, quantity squared. Square that -1/2 to get 1/4. And then subtract. What I did here was subtract 1/4 from both sides. So I have sine squared of theta is equal to 3/4. And then, of course, I need to get sine by itself because I'm just looking for sine of theta, not sine squared. So I get plus or minus the square root of 3 over 2. Square root of 3 is just square root of 3. Square root of 4 is 2. And since I'm in the second quadrant, I know that sine is going to be positive in the second quadrant. So I choose the positive value, square root of 3 over 2. Okay, so I want you guys to try this one. All right, your answer here should be A. Let me show you the work real quick. Okay, so again, I chose the identity that relates cosine and sine. And I plugged in my 1/3 for sine. 1/3 squared is 1/9. 1 minus 1/9 is 8/9. And when I take the square root, I get plus or minus the square root of 8 over the square root of 9. The square root of 8 is 2 square root of 2. Square root of 9 is 3. And since I'm here in the first quadrant, I'm going to choose the positive value of cosine. Okay, one more. All right, your answer here should be D. And you should have used the identity that relates secant and tangent. And this is your work. Since I'm talking about theta again in the first quadrant, I know secant is going to be positive, so I choose positive square root of 5. All right, the second skill we want to work on in this section is called simplifying expressions. Simplifying an expression means that you either simplify it down to a number or in terms of a single trig function, if possible. So basically you're making it as simple as you can. So let's take a look at this example here. We have the expression sine of theta times the quantity cosecant of theta minus sine of theta. Again, what are we doing? We are simplifying. Make sure you pay attention to the directions so that you know what's being asked of you whenever you have to do this. Okay, so notice what they're doing here. One strategy, I guess you could say, is to see if there's a way to rewrite any of your terms or any of your pieces in terms of sine and cosine. Sometimes that helps. So you should know that cosecant is the same as 1 over the sine of theta. So we're just replacing cosecant with 1 over the sine of theta. Now I have everything in terms of sine, but I still need to make it a little bit simpler. I need to make it as simple as possible. So what they're doing here is distributing the sine of theta to each term. Sine of theta over sine of theta is 1, so this term simplifies to 1. Then I have sine times sine, which is sine squared. And then this, you always look back at your identities chart to see if you can simplify. I know that cosine squared plus sine squared equals 1. So when I rearrange that identity, I get 1 minus the sine squared of theta equals cosine of theta. So again, I'm taking this identity, and I notice that if I subtract sine squared from both sides, 1 minus sine squared is the same as cosine squared. So that's as simple as I can get. All right, you guys, try this one. Tangent times cotangent. Okay, this is an interesting one because it actually should have simplified all the way down to 1. I'm going to show you the work. All right, ignore the scribbles. I was having some serious pen issues. So basically, I rewrite tangent of theta as sine of theta over cosine of theta times cotangent, which is cosine of theta over sine of theta. Sine of theta over sine of theta divides out to 1. Cosine of theta over cosine of theta divides out to 1. 1 times 1 over 1 times 1 is just 1. So in this case, obviously that's the simplest I can get because I reduced it down to a single number. All right, last example. This goes back to the equation we saw kind of at the very beginning. It says the amount of light that a source provides to a surface is called the illuminance. The illuminance, which we represent with the variable E, in foot candles is just a type of unit, on a surface is related to the distance r in feet from the light source. And this formula relates those things. The secant of theta equals I. I is the intensity of the light source measured in candles. Theta is the angle between the light and a line perpendicular to the surface. And again, E is the illuminance, right? We use this in situations where lighting is important, like photography and things like that. So we're going to solve this formula for R. That's my original equation. The secant of theta is the intensity over the illuminance times R squared. Remember that R is the distance in feet from the light source. So we're going to solve for R. Multiply each side by ER squared. And then we're replacing secant with 1 over cosine. Sometimes it's easier to deal with sine and cosine. Divide each side by E. And then multiply each side by the cosine of theta. So I'm trying to get R by itself, so I need to get rid of cosine. So I multiply by cosine. And then I have R squared is equal to this, but I need to get R by itself, so I take the square root. I'm only going to take the positive square root because in this situation I know that R is distance, and distance can only be positive. So is the equation in part A equivalent to this equation? So here they're giving me another equation. They're asking me if they are the same. So here's the equation I'm given here. We're going to see if we can rewrite it like the equation in the first part of our question. So I cross multiply. E times R squared equals 1 times I secant theta. Divide by E. So I'm trying to put it back in the form kind of the first equation. And I take the square root of each side. And I can see that when I solve the equation they just gave me for R, it's not the same as the one that I solved for R in part A. This is the one from part A. This is the one from part B. They are not the same. Okay, solve this formula in terms of D. All right, in this case, you should have gotten A. And here's the work to get to that. So I multiplied both sides by D squared. Notice I ended up with cotangent in the denominator. That's not necessarily wrong, it's just not one of my options. So I remember that 1 over cotangent is the same as tangent, and I just rewrite it with tangent instead, and then I take the square root.